Good morning. My name is Justin Cohen, and with this talk, I am going to try to offend as many of my fellow program managers as possible. Because I have to say, photonics is kind of boring. It's just light going through waveguides, right? Quantum, also boring. We've had this physics locked down for 100 years. Somehow, though, when we combine these two topics, you end up with a platform with the most transformative potential for technological change since CMOS. And that's why I want you to work with me on quantum photonic microsystems. We are just getting started on pushing on this intersection of quantum photonic microsystems with ongoing programs like the Griffin program, using lasers and integrated photonics to generate microwaves at the quantum limit of ultra-low noise performance to allow us to radically rethink the way that we build radar and RF systems. And with the Inspired program, looking to use non-classical squeezed states of light to break past the quantum limit in sensitivity for optical sensing applications. What's next? Now that we're getting a handle on how to engineer, generate, and manipulate exquisite, complex quantum states of light, we have the opportunity to revolutionize quantum sensing and sensing in general by endowing these devices with entanglement, the quintessential feature of quantum mechanics, enabling completely new modalities for how we glean data from the physical world. And in quantum computing, opening up the possibility for radically new heterogeneous architectures that exceed the individual performance constraints and scaling limitations of individual qubit species by mapping quantum information between these disparate technologies. And this is, in fact, MTO's latest program, Heterogeneous Architectures for Quantum. We announced HARC formally a couple of days ago, so I'm super excited to be with all of you here today to invite you personally on this journey with us to define a new era for quantum computing. Please follow this QR code to learn more about this broad-ranging program covering a huge array of topics in quantum computing, ranging from architectures, algorithms, quantum circuit compilers, resources, interconnect components, and quantum networking. And to learn more about our upcoming Proposers Day in a couple of weeks. So we're pursuing HARC in the context of this global race to develop a quantum computer with undisputed quantum advantages compared to what classical computers are capable of. But what we don't talk often enough, though, is that we already have quantum advantage for other technologies. And while there's raging debate going on in quantum computing about what success looks like in that field, we know what success looks like from other quantum technologies. Devices like transistors, lasers, and MRI systems take advantage of energy quantization to provide undisputed quantum advantages compared to competitor technologies, even if we don't normally think about these technologies as quantum or brand them that way. And we're in the midst of another wave of quantum technologies in quantum sensing, whether these are atomic and optical clocks, electric field sensors, magnetic field sensors, gravimeters, and so on, that also take advantage of energy quantization. So as excited as I am about the power of these technologies in quantum sensing and the transformative, game-changing capabilities that they're going to be bringing to our warfighters in a real sense very soon, thanks to a series of programs and innovations from many in this room, these technologies are barely quantum, no more so than the devices on the top that we've had for decades. I'd like to ask, how about we have sensors that are actually quantum, that take full advantage of the full breadth of quantum mechanical physics, and especially entanglement. So entanglement is typically the purview of the quantum information field, and which has benefited tremendously from the foundation that quantum sensing has provided. But now it's time to take lessons learned from quantum information and apply them back into sensing. So what might entanglement in sensing look like? This could look like taking the error correction and quantum control techniques from the quantum computing field and applying them in the forms of new codes and new control algorithms onto sensor qubits, running gate operations on these qubits and doing information processing on these sensor qubits. It also might look like taking the entanglement distribution methods from quantum secure communication field and applying them to network huge arrays of sensing devices that could potentially scale to the size of the Earth. And really this direction is all about applying the tools of quantum information science to practical sensing applications. I like to think about all of these new potential directions as variations on different heterogeneous quantum systems that take diverse qubit technologies, whether they're photons, atoms, ions, superconducting devices, or material defects, and cobbling these diverse technologies together in different ways. We could have arrays of the same atomic sensor qubits, potentially magnetometers, that are entangled via light. We could imagine entangling many different modes of qubits, pursuing different sensing modalities to do multimodal sensing, to tease out new information or even decorrelate the different sources of noise that afflict these sensors, and potentially even feeding the raw quantum data from these sensors and doing information on them in the quantum domain in the form of quantum information processing, or even feeding these data back into quantum computing, whether this is heterogeneous or otherwise. So these concepts could become more than just poor PowerPoint drawings, thanks to some key advances in quantum integrated photonics. With quantum photonics, it's now possible to imagine building large-scale circuits to combine large numbers of qubit technologies, whether these are manufactured devices like color centers or natural qubits like atoms that we interface through quantum integrated photonic circuits. You might know, though, that most of these devices operate at vastly different wavelengths, and most of them aren't in the telecom band that's received the lion's share of R&D investment for integrated photonics. So really we need to also turn to the nonlinear photonics tools and visible integrated photonics that are now starting to come online through new processes and new material platforms to be able to potentially do this in the quantum domain. And by combining these vastly different functionalities into something like a hybrid quantum microsystem could enable us to have a scalable and manufacturable platform to go pursue these brand new sensing and compute modalities. Okay, so now that I got quantum photonics out of my system, what other physics can we start to imagine building into microsystems? So I'll touch on a few other more nascent ideas in incubation here that I'd love to chat with you all about more. So in ultrafast optics, we have some amazing capabilities to generate incredibly high pulse powers and incredibly short pulse widths. And this is why this field has attracted several of the Nobel prizes in physics over the past several years. But it still typically requires dialing up by hand and an exquisite system in a lab environment. Is it possible to envision ultra-fast optical microsystems where we don't just get smaller form factor and more robust capabilities, but potentially leverage other unique features of integrated photonics, like the ability to rapidly reconfigure through electronics the output of such a laser? Now that we have some really cool demonstrations making ultra-fast optical devices out of the materials of choice from the ultra-fast world, but in an integrated photonics platform using materials like titanium sapphire or rare earth ions, this vision might be possible. What else? So in MEMS and acoustics, we have some of the world's best RF filters. And this is why mobile device manufacturers go to the trouble of packaging them up with larger scale circuits in larger assemblies. What if we could go beyond a discrete MEMS and acoustic device and actually get into the realm of fully capable acoustic circuits? And what new applications could we open up either in RF, optical, or even all acoustic processing? So based on some really cool device demonstrations in the field of acousto-electrics, acousto-optics, this vision might be able to be realizable as well. The last kind of main topic I'd like to leave you with is a question. What should we be thinking about next? What is the next integrated photonics platform that we should be pursuing? And when you consider that question, I'd like you to consider more than just the the next shiny new optical material that might enhance some specific optical parameter, whether that's a nonlinear effect or a loss effect, but really think about what this kind of switch could mean for manufacturing. I believe that there are lessons learned that we can learn in integrated photonics from other methods of mass manufacturing in optics. Integrated photonics isn't the only mass manufacturable optical technology. We've had fiber manufacturing for decades, and we've produced cumulatively enough optical fiber to stretch between the Earth and the sun many times over, using sophisticated glass material processing and manipulation. So we have a very cool project going on right now that is combining the glass processing techniques from fiber manufacturing with the semiconductor processing that is more traditional in integrated photonics to realize devices that are setting record performance in loss performance, as well as demonstrating robustness against fabrication variation, potentially opening up a new category of processing techniques that don't need the process control of high volume foundries. So believe it or not, I still haven't talked to you about all of the different directions I hope that we can take optical microsystems, so I won't read this whole list, but simply ask that if any of these are interesting to you or you have ideas in any of these directions, please come find me, come talk to me later. I would love to get your help on defining the future of optical microsystems and quantum technologies. Thank you.